Welcome to This Explainer. Right now, we're going to explore how the very nature of chemical discovery is undergoing a radical and honestly beautiful transformation. I want you to think for a second about the modern world around you. Literally everything, from the high-capacity battery powering your smartphone to the synthetic fibers in your running shoes, all the way to the life-saving medicines sitting in your cabinet right now, all of it comes from the atomic world. And for centuries, manipulating that atomic world has been an incredibly grueling science. We're talking heavy physical labor, empirical guesswork, and agonizingly slow trial and error. But today, we are witnessing a true revolution in how we design and build the chemical foundation of our lives. So, what actually happens when you give an artificial intelligence the keys to a chemistry lab? It's a question that is currently reshaping our entire world. We are rapidly shifting away from that old-school, traditional trial and error approach and moving straight into a brand new era of self-driving laboratories. We are combining human ingenuity with machine precision in ways that were practically unimaginable even a decade ago. You see, it's no longer just about software living on a computer screen. It's about software literally reaching out and manipulating the physical universe. You know that classic philosophy of mens et manus, mind and hand? It goes all the way back to the founding of pioneering engineering institutions in the 1850s. It's this foundational idea of learning by thinking and doing, applying theoretical knowledge to practical execution. But today, this whole philosophy is getting a massive upgrade. The mind is now augmented by incredibly powerful artificial intelligence, and the hand is augmented by autonomous, tireless robotics. Just picture a dedicated grad student working in a lab 2 in the morning, absolutely battling fatigue. Now, replace that with a system that never sleeps, never needs a coffee break, and literally never makes a pipetting error. It's a real night and day comparison. On one side, we have traditional chemistry, manual, human speed science that relies heavily on extreme physical safety precautions and slow trial and error. And on the flip side, we have modern chemistry, fully automated, data-driven chemical manufacturing. We're talking about a massive paradigm shift, transitioning from a world of manual guesswork to intelligent, rapid-fire innovation, where the pace of discovery isn't just faster, it's multiplied exponentially. Section 1, the Classical Chemistry Lab. Let's just briefly ground ourselves in the past. When you picture a classical chemistry lab, you probably imagine glass beakers, heavy fume hoods, and serious physical hazards, right? And strictly following standard safety guidelines requires cumbersome protective gear, intense handling limits, and the incredibly careful manual disposal of hazardous waste. Traditional chemistry is inherently dangerous, for sure, but more fundamentally, it is just extremely slow. Because we're limited by human physical constraints and the constant pressing need for safety oversight, a brilliantly trained scientist might only be able to pull off 1 or 2 complex reactions in an entire day. Section 2, the discovery bottleneck. Here's the thing. Exploring the vast universe of chemical space to solve modern global challenges is simply way too big a job for manual effort alone anymore. Just consider this absolutely mind-blowing reality. If you take just 1% of the carbon from a barrel of oil and you use it to make highly efficient thin-film solar cells, you get 10,000 times more energy over a single year than if you just burned that whole barrel. I mean, that is huge. This matters deeply because finding these hyper-efficient materials, whether it's for clean energy, carbon capture, or revolutionary new drugs, is the absolute bottleneck we've got to overcome. Finding the right molecule is exactly like finding a specific needle in a cosmic haystack. And guys, we just can't search that haystack by hand anymore. Section 3. Enter the AI chemist. Bringing artificial intelligence out of the software realm and dropping it straight into the realm of physical matter is our ultimate solution here. AI is seamlessly stepping in to take over incredibly complex tasks. It's handling reaction prediction, catalyst design, and this really cool concept called mechanistic insight. You can think of mechanistic insight as understanding the intricate step-by-step dance of atoms during a reaction. By doing all the heavy computational lifting, the AI can instantly suggest the most efficient, cost-effective, and environmentally benign pathways to synthesize incredibly complex molecules. So, how exactly are we achieving this leap? Largely through large language models. Yes, similar to the tech behind chatbots. Just like learning English, AI is learning to speak the fluencies of chemistry. It reads vast databases of chemical text and notation, such as SMILE strings. If you aren't familiar with that term, a SMILE string is just a clever way of translating a complex 3-dimensional molecule into a simple string of text characters. Just like letters make up words, these text strings allow the AI to literally read the chemistry, predict molecular properties, and eventually write completely novel synthetic pathways using the fundamental grammar of atomic structure. It's wild. Now, what happens when you combine computational chemistry, advanced catalysts, and artificial intelligence? You get an incredibly powerful synergy. Historically, running accurate quantum simulations of molecules was super computationally intensive, meaning it was incredibly accurate, but painfully slow. Sometimes it took supercomputers months just to figure out one single reaction. Well, AI acts as the bridge. By blending machine learning with these deep computational methods, we get the pinpoint accuracy of quantum physics with the blazing speed of an algorithm. This is what allows us to discover sustainable catalysts for energy and pharmaceuticals at a pace that, honestly, used to be pure science fiction. Section 4. Rise of autonomous labs. All this synergy is now building out into the physical world through fully autonomous robotic laboratories. I want you to imagine a relentless closed-loop engine of discovery. First step, the AI dreams up a chemical route. Second step, a robotic arm physically executes the reaction in the lab, mixing the precise liquids and powders. Third, real-time data is collected and analyzed by the system on the fly. And finally, step 4, the AI instantly refines its model based on those exact results. It's an unbroken, continuous cycle where machines experiment, learn, and iterate without any human intervention at all. Running 24 hours a day, 7 days a week, that changes literally everything about how quickly we can innovate. 688. That is the staggering number of continuous experiments autonomously conducted by the University of Liverpool's robotic chemist over an 8-day period. By integrating machine learning with robotic automation, this system optimized a photocatalytic reaction, which is just a fancy term for a reaction triggered by light, 10 times faster than manual human methods. The machine is happily plugging away, doing the grueling, repetitive bench work, while the human chemist gets to step back and focus entirely on the creative big picture. Actually, scratch that. It gets even wilder. Today, advanced automated systems can screen up to 10,000 different catalyst scenarios in a single day. No joke. That massive scale of high-throughput testing, paired with reinforcement learning, is completely revolutionizing the pipeline. It drastically shrinks the timeline from having a theoretical idea sitting in a computer to actually holding a physical, world-changing product in your hand. We're talking about significantly faster cures for diseases and way faster deployments of clean energy technologies. Section 5. Virtual factories and digital twins. So we've got the discovery, right? But how do we safely scale these molecular discoveries up to massive industrial manufacturing? The answer lies in creating virtual factories, specifically using something called a digital twin. A digital twin is exactly what it sounds like. A dynamic, living virtual model of a physical chemical plant. Think of it kind of like an incredibly high-tech flight simulator, but for a massive factory. By synchronizing with real-time data from physical sensors, the AI can simulate operations, predict dangerous equipment failures, and catch batch variability in the virtual simulator long before anything ever goes wrong in the real world. And the results are already here. Digital twins are actively helping chemical giants like BASF and Dow reduce unplanned downtime by a massive 30 to 50%. By acting as a predictive safety net, this technology is saving these companies millions of dollars. But honestly, more importantly for the rest of us, it means massive reductions in energy waste and carbon emissions, alongside much lower costs for the everyday consumer goods these plants produce. It's a tremendous, game-changing shift toward intelligent, resilient, and highly sustainable mass production. Section 6. The Future of Chemical Design. As we look out onto the horizon, we're eagerly anticipating the integration of quantum computing right into our chemical AI workflows. Quantum-enhanced machine learning will very soon allow us to model incredibly complex electron interactions with a level of precision we've never seen before. It will allow us to seamlessly design homogeneous catalysts, which are essentially perfectly mixed catalysts operating in the same phase as the reaction, kind of like dissolving sugar in hot tea. When true quantum advantage fully arrives, it's going to instantly solve chemistry problems that would take our current best supercomputers thousands of years to compute. It's going to accelerate molecular design to heights well beyond the limits of classical computing. So with AI, robotic automation, and soon quantum computing completely conquering the physical limitations of the past, the fundamental reality of science has shifted. The bottleneck is gone. The tools are here. The question is honestly no longer can we make it, but what should we make next? We now live in an era of true atomic design, where we have the tools to theoretically place atoms exactly where we want them to solve our greatest global challenges. So what global problem will you tackle first with these incredible new tools? Thanks so much for joining me for this explainer, and I'll catch you next time.